Hello, this is Peter from Educomondo and a warm welcome to our STEAM project number 9, teacher edition, called The Laser Bar. This series is for the very beginning STEAM teacher. No prior knowledge of programming or electronics is required. We call this level the Explorer level. Today we are exploring with our students the world of zeros and ones, which make up for the basis of all computers. We will teach them to calculate with zeros and ones, also known as the binary system. We will introduce a new component, the shift register. This component is known as the 74HC595. We will step up our student skills to build quite a complex project with a lot of components and jumper wires on our breadboard. And to program the shift register, we will teach some new functions such as shift out. We are all familiar with the decimal system to conduct our day-to-day calculations. However, computers don't work with decimal numbers. They can only deal with zeros and ones, and this at an incredible speed. So what is the decimal system? We use the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 to represent all the numbers we need. Once we are at 9, we go to the next level. The place of the digit in the number defines whether they are tens, hundreds, thousands, and so on. With binary numbers, the same principle applies. The first position is either a 0 or a 1. To arrive at 2, we need to go to the next position to the left. So 2 will be written as 0, 1. 3 will be written as 1, 1. 4 as 1, 0, 0. 5 as 1, 0, 1. 6 as 1, 1, 0. 7 as 1, 1, 1. 8 will be 1, 0, 0, 0. 9 will be 1, 0, 0, 1. 10 will be 1, 0, 1, 0. 11 is written as 1, 0, 1, 1. 12 as 1, 1, 0, 0. 13 as 1, 1, 0, 1. 14 as 1, 1, 1, 0. And 15 as 1, 1, 1, 1. So this is for the first 4 digits. This reasoning continues for 8, 16 or more positions that will allow us to create larger and larger numbers just by using zeros and ones. For our experiment, it is useful to continue with your class to cover 8 digits and calculate with them that 1111111 equals 255 in the decimal system. Why is this useful? Replace 0 with off or low and 1 with on or high, and you can see that by sending a series of zeros and ones to a digital pin on the Arduino, we can control a series of LEDs. As long as there are not too many LEDs, we are able to connect them to the digital pins of the microcontroller. But once there are more LEDs than available pins, the use of a shift register is the solution. So let's take a closer look at this component. Make sure that you have the right component. The type of chip is printed on the top. One of the most commonly available shift registers is called the 74HC595. The notch that you can see here indicates the top of the shift register. This is your reference point to start counting the 16 legs. Let's have a look at what these 16 legs stand for. Legs 1 till 7 on the left side are 7 output pins, for instance to link to 7 LEDs. Leg number 8 is the ground pin. We move to the other side of the shift register to pin 9. Pin 9 is an output pin to link to another shift register. Linking shift registers with each other make it possible to control 16, 24 or more LEDs. Moving up, we arrive at pin 10, which is the master reset or reclear pin. You notice that there is a line above MR. This indicates that it is active when set to low. Setting to low means connecting the pin to the ground. Pin 11 is the clock pin. This is an input pin that will receive the clock signal from the microcontroller. Pin 12 is the latch pin, also called the register storage clock pin. This is also an input pin that receives the latch pulse to release the storage to the output pins. Pin 13 is the output enable. This pin is also identified with a line above OE, which means that it is active when low, in other words, when connected to the ground. Pin 14 is the serial input. This is the gate that receives all the zeros and ones from the microcontroller. It receives the data 1 bit, a 0 or a 1 at a time. We call that serial. The shift register will output that series of zeros and ones in one go to all 8 output pins. We call that parallel. And that is also the reason why we call this type of shift register a serial to parallel shift register. But wait, don't we only have 7 output pins on the left side of the shift register? Indeed, but pin 15 is another output pin. Actually, it is the first output pin referred to as pin number 0. The last pin, pin number 16, is the positive voltage supply pin. Let's take a closer look at the logical sequence of what happens to our zeros and ones. The data is sent to pin number 14. The clock signal ensures that the data is sent in an orderly way. Compare this to the beat or the rhythm of a song. Each time a series of 8 bits has been received in the shift register's memory, the latch signal triggers the data to be released to the storage register, which in turn triggers the 8 output pins. Sending a sequence of, for instance, 01, 01, 01, 01 will light up every other LED, as you can see on the animated view. Now that you have explained to your class the inner working and purpose of the shift register, your class is ready to start building their own projects. Because this is quite a complex build, we suggest to prepare in advance the sets, otherwise you might lose too much time. First, the microcontroller and the breadboard. You notice that for this lesson we are using a larger breadboard that is mounted on a larger project plate. You also notice that for this lesson we are using for the very first time the brand new Arduino R4 Uno Minima. Of course, you can still use the trusted Arduino Uno R3 or any of the other quality brands that make their own microcontrollers, since Arduino is an open source hardware platform. We also hand out 8 red LEDs, 4 blue LEDs, 8 resistors of 220 ohm, 3 jumper wires of the same color, a red and a black jumper wire, 8 of these long preformed wires. These wires are very useful in more complex projects as they will keep your build clean and clear. 5 shorter of these preformed wires, and the most important, the cardboard laser bar. Show your class this fritzing drawing. While referring to this drawing, you can explain to your class how to build the project. The shift register is pushed in the breadboard in such a way that it bridges the gap in the middle of the breadboard. Next, we install the LEDs. We start with a blue LED, followed by a red LED. The negative legs are pushed into common negative rail on the side of the breadboard. The positive sides go into the main section. Each time we allow for a space of 2 holes. Once we have pushed all the LEDs in the breadboard, we connect the resistors to the positive legs of the LEDs. Make sure that your students know that they have to bridge the gap on the breadboard, otherwise they simply short-circuit the resistor. Next, we connect the resistors to the output pins on the shift register. Leg 15, or output 0, goes to the first blue LED. Output 1 goes to the first red LED. Output 2 goes to the second blue LED. And output 3 goes to the second red LED. And so on till we have reached output 7. We use one of the small preformed wires to connect pin 8 to the negative rail on the side. And another preformed wire is used to connect the bottom and top ground rails. We don't use pin number 9 as we will only be using one shift register. We don't want to reset the shift register, so pin number 10 has to be set to high, which means that we connect it to the positive rail. The clock pin number 11 goes to the Arduino pin 9 and the latch pin number 12 goes to the Arduino pin 11. Pin number 13 is the output enable, and it is active when set to low. We connect pin 13 to the negative or ground rail of the breadboard. Pin number 14 is the data pin, and we connect this to the Arduino pin number 12. Next, we connect pin 16 to the positive rail. And lastly, we connect the negative rail of the breadboard to one of the Arduino ground pins and the positive rail to the 5-volt pin. Once all of that is completed, the cardboard laser bar can be mounted over the LEDs. Now your class is ready to start the Arduino integrated development environment. We give our file a name, and we do that in the space above the setup area. We call this file Project 9 Laser Bar. And next we create another command line, variables. We need to define the 3 pins that we use on the Arduino. So we call them INT latch pin equals 11, INT clock pin equals 9, INT data pin equals 12. And of course, don't forget to close the command line with a semicolon. Here we can already define a delay time, and we can set it at 250 milliseconds. So int dt equals 250, ending with a semicolon. We are going to send a sequence of 8 bits to the shift register, and to do that, we have to tell the Arduino that what we are sending is not an integer, but a byte. And we also need to inform the Arduino that it is a binary. And we do that by adding 0b before the sequence of the zeros and ones that we will send. So byte LEDs underscore 1 equals 0b 01 01 01 01. We want to create the effect of alternating LEDs going on and off by adding another line sending exactly the opposite. So when we first send a 0, we now send a 1. Byte LEDs underscore 2 equals 0b 10 10 10 10. In the setup space, we declare our pins using the pin mode command. All of the pins are output pins. So we use pin mode and in between brackets latch pin output, pin mode clock pin output, and pin mode data pin output. In the loop section, we first set the latch pin to low. So digital write, latch pin low. And here is a new command specifically related to control the shift register. Shift out, and in between brackets, data pin, clock pin, LSB first, LEDs underscore 1, ending with a semicolon. LSB stands for least significant bit. Once the series of LEDs 1 is sent, we have to set the latch pin to high, so that the shift register knows to release the bits to the next memory. So digital write, latch pin high. To slow down the process so that we can actually observe what is happening, we add a delay with a variable dt. For the next series, we simply copy the code and change LEDs underscore 1 with LEDs underscore 2. So we get digital write setting the latch pin to low, shift out, data pin, clock pin, least significant bit first, and now we send the series of the LEDs underscore 2. We set the latch pin high again, and we also introduce another delay. That completes the programming, and your class is now ready to upload it. Although the program in itself was not very complex, building the project was quite difficult. Hopefully it works for all of your students. We used in this lesson a large breadboard, but you can also use a smaller one, as you can see from this build. If it doesn't work, tell your students not to panic. Step-by-step diagnostics is one of the most important skills in programming. Let them systematically check what was the error code in the Arduino IDE. Did you end all commands with a semicolon? Did you type all commands correctly? Did you put the wires in the right pin? Did you declare the right pin numbers as variables? Are all connections on the breadboard firm? Are none of the LEDs or resistors broken? We have come all this way to build a very nice project. We can ask ourselves, what else can we do with it? Since we talked about binary numbers, we can use the very same project to build a binary counter. What is a binary counter? Let's go back to the whiteboard and draw the 8 positions of our LEDs. Each position represents a level in the binary system. So 0 will be all LEDs off or set to 0. 1 will be the first LED on and the others off. 2 will be the second LED on and all the others off. 3 will be the second and the first LED on and all others off. 4 will be the third LED on and the rest off. 5 will be the third and the first LED on, the rest off, and so on till all LEDs are on. Ask your class whether they still remember what number this represents in the decimal system. Indeed, it is number 255. Let's shift from the whiteboard to the project board. Let your class remove the cardboard figure and replace the 4 blue LEDs with 4 red LEDs. In the IDE, we will make some changes to the program. Let your students discuss among themselves how they would approach this task. They already know all the basic functions to make this small change happen. Give them a couple of minutes and ask some volunteers to explain what they would do. The first step is to remove the code that refers to the second row of LEDs. We don't create any alternative blinking, so only one row of LEDs needs to be taken into account. We just need LEDs as a variable. The second step is to set all the bits to 0. We know that all of them work from the previous project. Alternatively, you could set all the bits to 1 to check whether all of the LEDs are functional. The third step is to delete the code in the loop section that refers to the second LEDs_2 and replace LEDs_1 with simply LEDs. And last, just add the command LEDs equals to LEDs plus 1. We also want to check our binary counter on the serial monitor. Here we can do a couple of interesting things. First, we have to put in the setup section the command serial.begin 9600. And in the loop section, we add a couple of print commands. Serial.print, what do we want to print? We want to print the LEDs, and we want it to be printed as a binary code. So we have to add BIN in the brackets. We have to add BIN to tell that it is a binary number that has to be printed. If you want to have it expressed also in a decimal number, we add serial.print, and in between brackets and hyphenated, we include equal sign. And then we end with serial.print line, and then we just say LEDs. When we open the serial monitor, we see our binary counter going from 0 to 255, and each of the binary strings is also written in its decimal format. Because we created a laser bar, let's give your class an assignment on what lasers are. What does the word laser stand for? What are lasers used for? Give a couple of examples. Can you give the titles of 2 movies where lasers and laser beams are prominently used? And why should you never point a laser light into someone's eyes? Have fun with the assignment. And again, these were just a couple of suggestions. By all means, use your own creativity. I hope you and your class have enjoyed this project. I think they can be really proud because this project was quite difficult to build. We are now ready to start our 10th lesson. In that lesson, we will introduce again the new component, the push button. I am really looking forward to meet you in our next project called the desktop lamp. Bye bye for now.